Okay, so for today, let's continue with space frame analysis. So I'll continue now with 3D space frame. Okay, so this is the default stiffness matrix that STAAD is generating when you model your structure in 3D. Okay, so what's the local stiffness matrix? So this is the local stiffness matrix of a line element or a beam element in 3D. If you notice, it's now 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is now a 12 by 12 stiffness matrix because so this is the again this is the 12 by 12 stiffness matrix because in general we have these forces acting on our member. So we have force along the longitudinal axis, the shearing force parallel to local y and z, and of course there are moments about the z-axis, moment about the y-axis, and moment about the x-axis. So mx is actually what we know as torsion. Okay, and mz is what we know as the bending moment that we need in our design. Okay, and this Fy and F2 are the shearing forces, while Fx is the axial force. Okay, so we have 6. So therefore, we have 6 on both ends of the member. So 6 plus 6 is 12 uh, in each element. So 6 per node. And then we also, similar to the previous topic, we also have a transformation matrix in a space frame, and these are the formula for that. So this is also 12 by 12. Okay, because we will be using again uh, the formula T transpose KT, which is this is the local axis and this is the transformation matrix. Okay, so we need this matrix in order to generate the transformation matrix. For the RXX, again these formulas I also got from Casimali. For the RXX, it's a formula. So cosine theta x. So that means if this is Rx, if you wanted to find Ry, so that will be theta y. If you are getting Rz here, Rz, that will be theta z. So okay, because we are getting this formula only pertains to Rx. Okay, that's why you get the theta relative to the x-axis. Okay, so of course the length is based on Pythagorean theorem. Okay, so we know that. So for our sample problem, I modeled this in STAAD. It's a 3-member space frame, which is this. Okay, then our cross section is 300 by 400. Beam. So the material is a steel, and these are my corresponding properties. It's all 5 meters. Elasticity is 205 gigapascal. G is the modulus of rigidity, right? Modulus of rigidity. This one is modulus of elasticity. So since we are now considering ano, right? We are now considering torsion. That means we will be needing this. Okay, and of course the J, moment of inertia. Okay, IZ is the strong axis moment of inertia. Since our cross section is 300 by 400, so if you get the moment of inertia of that, BH cube over 12, right? BH cube over 12, you will get this. While IY is HB cube over 12. You will get that. And area is 120 because this is 300 by 400. Let me check. Yeah, okay. 120. Okay, so this is my code for that. There. So I just implemented this this one. Okay, I need to erase this. So it's a 12 by 12. So this is too large. That one. Oops. Okay. So I have, wait. So K11 is this one, 12IZ is this one, 12IY is this one, GJL squared over E is this one. Okay. So let me check. K11 AL squared, AL squared. 12IZ K22 is this one. 12IY is this one. K33. K44 GJL squared, that one. Okay. So that's how I implemented in SMAT. And my BU matrix, remember, since our members this one, so this is my, I think my member 1, member 2, member 3. Therefore I assume that seven, 8, 9, 10, 11, 12. For member 1, this will be my 1, 2, 3, and rotation, no? Okay, say 4. I think this is 6. No, this is 6. So this is 4, rotation here 5. And then of course this will become 7, 8, 9. And then the 3 rotations. Okay. If this is my X, say Y. 7, 8, 9. 7, 8, 9. then 10, 11, and then 12. That's why what remains, since we are getting this displacements here, that will be 7, 8, 9, 10, 11, 12, right? So that means my 1 to 6 here is here, and then my degrees, the code 1 to 6 for member 2 is here. So everything 7 to 12 is in this joint. Okay, for member 1, for member 2, and then for member 3. And since the S matrix will be 6 by 6, because we are only getting the displacements on this joint, and that will be 6 displacement, 3 translation, 3 rotation, so 6 by 6. And these are the locations. Okay, now for this one, the rotation matrix, in order to get the transformation matrix, I'd like you to recall this. This is the transformation matrix. Now for member 1, since our, remember our x, so our, say, beginning is 0, our end is 5, and the total length is also 5. That means this value is 1, right? 5 over 5 is 1. Therefore, substituting Rxx to this general formula here, not this one, this one. So this is the general formula. So I already get Rxs as 1. Therefore, other Rxy, Rxj is 0. Because it's we are no, because the member 1 is a horizontal member, so you don't have Rxy and Rxj. Okay, so that is 1 here. So this one is this one, which is also 1, and this one is also 1, because other values are 0. Because Rxy here is 0, Rxj here is 0, so this is 0. Okay, and this symbol here is the, basically this is analogous to the beta angle in STAAD. So the beta angle of the axis, of the local axis. So we do not consider that yet in this problem, so we don't have a beta angle, so that's why it's still 1. Okay, now for vertical member, for member 2, this will be our formula, so which is 8.7. Where is 8.7? Okay, where is equation 8.7? This one. So this is the rotational matrix for vertical members, equation 8.7. Okay, because we don't have Rxx, so we only have Rxy, which is 1. Okay, because the member is vertical, so the y, so this is 0, and your y here is, say, 5. That is also the length, so 5 over 5 is 1. So Rxy is 1. Rxy here is, for vertical members, this one is 90 degree. Okay, so cosine 90 is 0, so this is 0. Sine 90 is 1. Sine 90 is 1, and then cosine 90 is 0. Okay, so similar approach for member along the z-axis. Okay, along the z-axis, where is along the z-axis? That one. Okay, so for member along z-axis, so this will now be 1 because you have value on rxa. Okay, so this is 1. Okay, and this is 1 and this is 1. Okay, so when you know that already, I now open my SMAT here. Oops, here. So we already established K here, and my BU and BB matrix already established, and prepare a null matrix 6 by 6, and this is our rotational matrix, and this is the code for getting the transformation matrix. Okay, which is from here. Then that's it. Once you know the transformation matrix and the local stiffness matrix, you can generate the global stiffness matrix. And get the structure stiffness matrix. Okay, and this is my applied load. Okay, so I applied, so this is 1, 2, 3, okay, 6. So that means I have an applied vertical load, negative 100, and a 150 kilonewton meter in our structure, which is this. Okay, so this is our applied our structure. Okay, and then so here's the model, this one. So where's the supports? Of course, supports are fixed. Loading is this one. Okay, so 100 kilonewton and 150 kilonewton meter. Then analyze, then post process. So I get this displacement. So I have a 0.003 and 0.015 xy displacement. What do we get in our code? So almost the same. Okay, 0.003 and 0.015. So yeah, so almost negligible z displacement. So that's why we don't have z displacement here. Okay, the rest are rotation. Now once we get the displacement, so say for member 1, this will be our member forces. So again, this is for this is member 1, member 2 is this, and member 3 is this one. Okay, so let's now check the reactions. Okay, so these are the reactions. Okay, for member 1, so I have 14, 26 x and y. So 14 and 26. Almost zero reaction, Fz. So this corresponds to the moment 45 kilonewton meter, which is almost the same. 45 kilonewton meter. For member 2, vertical 1, these are the reaction, right? So for the x, it's 14. Okay. For the y, 73. 72 in STAAD. And for the moment, it's also 24 kilonewton meter. Okay. And last, for member 3, okay, so these are the reactions. So if you notice, XYZ is almost 0, similar to here. But the moment is 13. So instead, I'm getting 11 or 10.5. My SMAT is 13. So there's a discrepancy because I'm only using limited decimal places. Okay, so that's it, and that's how you analyze a 3D space frame member, which is the default stiffness matrix that STAAD is actually um, using, in all line element. Okay, so if we translate that in as a forces, that's what we get. This one. Okay, so we can check, right? So if you notice, for the vertical reaction, so this is the 100 kilonewton, it's directly acting on this vertical member. That's why it gets the highest vertical reaction also, 78 for member 2. Okay, so sorry, 73 here. I forgot to update this one. For member 1, this is 26. It's the vertical reaction. That means for member 3, it's only contributing about 0.19 kilonewton. And then for the reaction, I'm getting 45. This one should be 45. And for member 2, I'm getting 24 here. Okay. And for sure, if you perform an equilibrium analysis, so you will this moment will counter the 150 kilonewton meter. Say for example, yeah, because it's in 3D. So if you sum up moment here, of course, you will also consider this forces. Okay, so that means that's how you analyze space frame member. So using a 12 by 12 stiffness matrix like this.